Korean?
Swedish?
Mandarin?
German?
I already asked for Korean. Mandarin, same thing.
That's all video. He was saying it's my friend.
What? They're just all the same. I mean, it's clear. Okay, so we're going to continue talking and leading up to our definition of conjugates, which will be the paths over which we integrate when we do line integrals. So yesterday we looked at paths that started at some point, say Z1 and went to a Z2, right? And then we had some orientation to it. And you followed the path along here, right? Which meant that, well, you had some time. And the time was going between 2 point A and B. And what you can think about it, instead of writing Z1 and Z2, you can think about it as Z is a function of t, and this is where the function is at A, and this is where the function is at time B. And we gave a nice formula for this. Say this line here is Z of A plus, or no, was it Z of A? Maybe it was Z of B? Or was it? What should it be? We know we're going to have to do...
Z of A.
Is it Z of A? Is it the starting point, the initial point?
Yes.
Okay. And then what do we do over here? Well, we better get the Z of B in.
Z of B minus Z of A times time.
Z of B minus Z of A times the time. Now is this right?
Well, you have to adjust the time a little depending on what the time is.
Yeah, right. If this was 0 to 1, then okay, when t is 0 you'd have Z of A, and when t is 1 you'd have Z of B. But it's not quite right when you're just going from A to B, you have to fiddle with things. So how do we fiddle with it? Well, it still should be the case that
minus A times the reciprocal of B.
at A you want this to be 0, so that the whole term goes away, and you're left with Z of A. At B, right, well you want it to be 1, so this would be B minus A, so you better multiply, as Christina said, by the reciprocal. You can put a 1 over B minus A in there. Okay, and that would do it. So this is a nice called parametrization. Big word, huh? It comes from parametric equations, yeah? Parametrization. We also talked about how to parameterize a circle. Yesterday we did it with radius 1, today to do one with radius 3. Doesn't really change anything. And let's say I want to traverse it counterclockwise. Then the Z of t should be what?
E to the I t.
3 even?
3, right? Because you want it to be radius 3, so you toss a 3 in there. And here Z is running between, or t is running between 0 and 2 pi. There's another parameterization. what if I didn't want to do this in the complex plane? What if I just wanted to do this in R2? So this over here is in C. Same problem. Circle with radius 3. So when you want to give a parameterization in R2, a nice way to do it is to tell you individually, right, I'm going to give you a parametric equation. I'm going to tell you individually x is a function of time and y is a function of time. So at time t, say that'll be the coordinate, still going in this direction. What is the x coordinate at time t?
Cosine squared of t.
So you think it's cosine squared? Let's see. And so this one would be
Sine squared.
sine squared. Okay. Now, is there anything missing?
3.
3, right? There's the radius. Fine. Is there anything superfluous? Actually, it's worse than superfluous. That shouldn't be here.
Squares.
Square, why not? How do you know that that square can't possibly be correct? We have to make your way all the way around, right? Now, cosine squared is always positive. So that if you did this, right, you'd always be on this side, right? And if you did this, you'd always be in this quadrant because you're already on this side. Now you have to be up here.
I'm just thinking cosine squared plus sine squared equals 1.
That's true. Cosine squared plus sine squared equals 1. But where does that come from? Well, it comes from the fact that the coordinate here is 3 cosine of t, comma 3 sine of t. And you know that points on the circle satisfy here x squared plus y squared equals 9. So 3 cosine squared plus 3 sine, or 9 cosine squared plus 9 sine squared equals 9. So cosine squared plus sine squared equals 1. That's where it's coming. Okay, so this is a real parameterization. So I want to start by writing down some definitions just for real stuff first, and then we'll come back to complex. And somebody wrote on their Facebook that their life had become far more difficult since they met A plus BI. Is that right? Something like this? No, I won't name any names.
Far more complex.
Far more complex. Maybe that's what it was. Yeah, far more complex. So for the time being, right, just for the beginning of today, we'll keep A plus BI out of this. So, problem? No? All right. So, part of what I'm going to be doing here is going to seem awfully boring for a while. And the reason why is because I'm going to need to lay down the definitions of words so that we can have a meaningful conversation about things without me just not knowing what, you guys not knowing what I'm talking about. So, so the first thing is we're going to be dealing with, as I said, parametric equations. So, this is where I give you two functions of t, x and y, and I let t run between two times, a and b. And these should be, for the purposes of what we want to do, continuous real functions. Okay? There's nothing complex about this.
You don't really enjoy that.
I do. So, the first thing that I want is, well, when you draw this, right, it's going to look like some shape, right? As you let, you think about somebody drawing it, and you start the stopwatch at A, and you let it end at B, and so you run these functions, and they do something.
I disagree.
Good. Okay, so something happens, and
Give it a shot.
what we're looking for is not just any old thing to happen. Okay? For instance, we're not terribly interested in any continuous real functions here. Okay? We want something a little bit nicer. So the first condition we're looking for is going to be called smooth. So what should smooth be? What do we mean by smooth? And I don't mean suave.
Like a beer.
We're not talking about how it goes down. So what do we want? Well, in calculus, we like, for instance, functions that don't
Continuous. Don't hop.
We want more than continuous. For instance, what's the worst? The first, I should say, bad function in calculus?
Absolute value x.
Absolute value of x, exactly. Why is that a bad function in calculus?
There's a point.
It's a point.
It has this little point, right? You get this little thing right there, right? This little corner. It's not differentiable there. We don't like that. So we don't want these sort of things. There's another one which we only talk about, but we never really give examples of in calculus, but they look like this.
Cusp.
It's called a cusp, right? So this is a corner, and this is a cusp. And the problem with either of these is you're not differentiable there. So we don't want to have to deal with paths that look like that.
What's cusp? E to the square root?
E to the x squared, that's okay.
The one you asked me to solve.
Yeah, that was what I wanted to
That
find
was-
the
that was
integral of
the
e to the x
cusp?
squared. No. That was just e to the x squared. A perfectly reasonable thing to ask and a perfectly unanswerable question in terms of elementary functions. Yeah. So we don't want these. So we rule them out, and so the functions that don't have that we're going to call smooth. Okay, they don't have these to them. They're just nice and smooth. So how, man? I mean, that's not terribly precise, right? I mean, this is a problem. I just say, is this function smooth? This doesn't. I haven't given you a real criterion, right?
Yeah, I haven't yet seen a function pick up any girls.
And you're young.
That's why I said yet.
So, smooth is going to mean that if you look at the derivatives of these functions, that these are continuous. And then there's one more thing. Okay, so it's not just that x and y are continuous. And it's not even just that they're differentiable. We really want that they have continuous derivatives. So they're really quite nice. And the second thing that we want, and this would not be an issue if we weren't talking about parametric equations, but you see, you think about this as a movie, right? Instead of thinking about the function or the path just being there all at once, it's kind of being created over time. That's the way you want to think about this. There's really a starting point and an end point. If I say f of x equals x squared, there's no starting point to that. Even if I give you a range, -1 to 4, there's really not a starting point. It's just there. It's all there at once. This, you really want to think about, there is actually some order to everything.
Like driving your car?
Yes, like driving a car, right? You drive to the grocery store. You start at home, you end up at the grocery store. You're not just driving the whole way at once. This doesn't exist all at once. You have to go
You
from A
can't
to
drive
B.
over corners and cusp because then you'd bottom out.
That's true. You really don't want to drive over corners. You can go around corners, but even then, as a car, you kind of hook around it, right?
Yeah.
You don't really. Except there was an old show in the '80s, which before any of you were born, called Auto Man, and it was this wonderful show about a crime-fighting hologram, and he had this car that he would drive, and he would make right-angle turns in it. And he had a guy who had invented him who would sit in the car with him, and when they would make the right angle turns, the guy would always fly into the window. It was a pretty cool show. Auto Man. And he always had great puns based on that. You know, like girls would come up to him and they'd say, "Can I have your autograph?" And he goes, "My autograph?" You know, just, he was Auto Man. Loved it. All right, so
Aside.
the second thing that we want is, because this is a movie going, right? When you go to the movies, something that very rarely ever happens is the movie stops in the middle of the movie, and you're sitting there in the theater, and all of a sudden, right, it just stops. Okay? This you don't want to happen, right? You don't want the whole movie to just stop. Okay? It might get boring. You know, the character development might be bad. There's no action, whatever. But at least the movie is going. You're getting closer to the end. Okay? We want the same thing to happen here. We never want it to be the case that everything just stops, grinds to a halt, and you just sit around for a few minutes, and then it takes off again. Okay? So in this way, it's not like driving a car. Because in driving a car, you have traffic lights, and you have to stop at those. Okay? We don't have traffic lights when we do this. Okay,
So yield signs.
Yeah. You have to slow down, but we can never stop. So x prime of t and y prime of t are not, or never, I should say, are never simultaneously 0 for t between a and b. Okay. Now it could be the case that the y coordinate isn't changing, right? And you're just going like this, or that the x coordinate isn't changing. That's fine. Are we?
Yes.
Oh, okay. Wow, that's a wide. That's cool. All right. So that's the two things we want. We don't want to have any sharp turns, right? No cusp, no corners, and we don't want the movie to stop. Okay. So that's what we mean by a smooth curve. That make sense? Mm-hmm. Cool. No problem. Okay, what's the second thing? Oh, the second thing, there's going to be a few of these times where I'm going to say something and then I'm going to immediately say something else that I'm not even going to write down so much because it's just so, I mean, you don't want to write down just the same thing over and over again. You can even guess what this is going to be. Piecewise smooth curve. What is a piecewise smooth? Well,
That's a really funky volume.
this is not good right here. Yeah. But between this point and this point, right, between A and B, you just have a nice smooth curve, right? Assume it goes that way, and there's no. You have to take it on faith that it doesn't stop. And then once you get to B and you turn around and go to C, there's a nice smooth curve between B and C. And then you have a circle, right? You go around and say that way. Okay, fine. And actually, here the terminal point and the end point are the same. We'll have to remember that. Okay, but the whole thing is not smooth. Okay, so piecewise smooth is when we join, I'll say this in words, because it's not that much of an advantage to write down it in math. We join together a finite number of smooth curves. Okay, so the mathematics is in the join together. So the intuition, and it's completely correct, is that when I say I'm joining together, say this curve, let's we call that C1 and this one, oh, that's a bad choice of letters. Take that as D. Okay, C2 and there's C3. When I join together C1 and C2, it means that the terminal point of C1 is the same as the initial point of C2. And the terminal point of C2 is the same as the initial point of C3. So that's what the join together means, is that terminal and initial points coincide appropriately.
But are they smooth at the terminal and initial points as well?
Don't have to be. Right? If they were smooth everywhere, then you could just make it one big smooth curve. But you see right here, this is probably not smooth. You're going around this corner.
I mean, you can join together two functions that are different functions, but smooth at the joining point.
I mean, all this is saying is that you might have things which are together not smooth. All right? And by together, and it would be at that joining point. But individually, if you forgot about that joining point, they are smooth. So then you call it piecewise smooth.
But they don't have to be smooth at the joining point.
It doesn't have to be smooth at the joining point.
So say if you were to break up absolute value of x into a piecewise defined function, would it be piecewise smooth then?
Yeah. Yeah, exactly, right? Because this is smooth, and this is smooth. So together it's piecewise smooth, right? Even as a whole, though, it's not smooth. Okay, but it's piecewise smooth. So piecewise smooth is a little bit weaker than smooth.
Okay. Because I was thinking like function 2x for up to 1, and then x squared for 1 and greater.
Yeah, so this wouldn't be. Well, assuming we didn't choose it amazingly appropriately, this would not be differentiable, say, at the point where they connect. Right? And so it wouldn't be smooth there. I imagine there is a point where we could possibly make it will actually work out. But,
Well, yeah, like what I just said.
no, I mean, even with those functions, did you say a point?
Yeah, I won.
Oh, at 1? Is that, let's see, yeah, the derivative. Yeah, that's right. Yes, of course. Yeah, this will work.
Jeez.
I didn't hear the echo on it.
Those were for you, really.
Probably use it.
Okay.
Hi.
Hello.
You missed some great, like, snapping at each other. I'm using this.
Okay, so speaking of simple, hi Valerie.
Hi, how are you? You want some notes?
All right, so the next thing is going to be a simple curve. What should a simple curve be? Well, this you should have no idea. There's nothing about the word that really tells you this is what it should be, or this is even what it could be. When you see the definition, you'll say, okay, sure, that's simple, fine. But you can't reverse engineer it.
Wait, is this part 3?
Oh, yeah, I forgot my number. The important numbering. So what should simple mean? Well, simple is just going to mean that the curve is not going to intersect itself. Okay, you're not going to have an 8, for instance. Okay, with one possible exception. Where is the one possible exception going to be? We do allow that the terminal and initial points coincide. Right, so a circle is allowed. It goes all the way around, and it intersects itself at the beginning. Okay.
So then an 8 could be possible.
No, because, well, let's see, actually, is that right? Could an 8 be possible? Let's see, let's draw it like, no, if you assume that the 8 has to intersect and then go down like that, then there's actually, it's not just the initial and the terminal point, there's a point in the middle. Yeah, that's true, but you still have to be able to draw it continuously. See when I hit it there? That's not the end of the game. Well, now let's see. Now, what if we start this way? No, you're definitely toast, right? Because you got to go around. As soon as you hit that point, that should be the end.
Yeah, then you just draw another circle.
Yes, but it's not a simple curve. That's the point.
Should be 2 simple curves.
Yes, but we want one simple curve. So simple is going to mean that you're not going to have any repeated points. So let's see. I just write it. No self-intersections. t between a and b, except possibly at xa, y of a, and x of b, y. That's the only one.
It's not.
It's really a question of one-to-oneness. Okay, the fourth one is going to be a closed curve. This one you might be able to guess.
Circle?
Yeah. What? So it doesn't have to be a circle, but a circle is an example. So what is it? So it's. We don't need to be so. I mean, we can be simpler than that, right? When you have a curve, we don't know a whole lot about it, but we know that it has, well, some parameterization. It has an initial point. It has a terminal point. If it's going to be closed, what? Are the same, exactly, right? Closed means that the initial point equals the terminal point.
But not any other points? So an 8 would not work?
No, an 8 would work. An 8 would work because all you need is that the initial point equals the terminal point.
And it can cross itself as many times as it wants.
Yep. You don't require it to be. We don't require it to be simple. Of course, you might want a simple closed curve.
Like a circle?
Sure, like a circle.
Wait, an oval?
An oval would work too.
A square?
A square would work too, except for, well, as long as we didn't want it to be smooth.
Yeah. Well, simple and closed do not include smooth.
Well, for now, no, let's keep that way. It's really a term, we only want to talk about smooth curves.
Well, that's very prejudiced of you.
I'm a prejudiced sort of guy. So you will not be surprised to find out that a curve is simple and closed if it's simple and closed.
No way.
No?
I
Okay.
don't believe you.
So this is a
I want you to prove it to me.
very thankfully definitions don't need to be proved. Okay. The next thing I want to talk about is orientation. And I know you can think of a lot of different kinds of orientation. It's a plural. But this isn't any of those. You see, when we drew this picture over to the left, we had these arrows that told you which direction you were going. And that makes a difference in this world, right? And if you think back to calculus, when you integrate a function from a to b, there's an important thing going on there. You're saying from a to b. You started a, you ended b. And this is not the same, in general, as the integral from b to a. In fact, well, what is the one is the opposite, right? The negation of the other. So in fact, it's equals the negative of it. So this negation is coming because you're reversing the orientation of the path. So we're going to have two kinds of orientation, positively oriented and negatively oriented. And positively oriented is going to mean we're, well, traveling from the initial point to the terminal point. So that when you put t equals a, you're at the initial point, and when t is equal to b, you're at the terminal point. So after I write this for positively oriented, I come up with a good, no, I just wrote positive orientation. For positively oriented, the path goes from the initial point to the terminal. Okay, so in other words, when t equals a, you're at the terminal. There, you're at the initial point. And when t equals b, you're at the terminal point.
Would that mean that you're at x of a, y of a?
Yep. Well, yeah, you're at that point. Let's write negatively down, and then well. So if we call the initial point A and the terminal point B, then so this is your initial. This is terminal. Then this curve is positively oriented if your parameterization goes in this direction. So, what's at stake here? We wrote down a parameterization for this curve. I should mention that there's more than one possible parameterization that you can write down for a given curve. Let me give you just a quick idea how you might do that. This is just a line segment, so we already know how to do a parameterization of it. But let's say I did the following. I used the following parameterization. Tan of t plus I tan of t. Let's say t here is going from 0 to pi over 4. So that when, say that's the point 0 and this is the point 1 plus I. So when t is 0, tan of 0 is 0. So this whole thing is 0. And when tan is pi over 4, you get tan of pi over 4 is 1. So you get 1 plus I. And since these are always the same value, it's going to be on this line. This is just sort of y equals x. So this is a completely different way of writing a parameterization of this line. Okay, so there's different parameterizations, and what you're really asking is, if I write down this curve and I write this direction down, is my parameterization going in the right direction? Does it start at the initial point and end at the terminal point? If I drew my arrow on here like this, said, okay, this is how I want to proceed along this path. Is this a positively oriented parameterization? And the answer is no. Why? Because this thing starts at 0 and ends up at 1 plus pi as you follow t. But this thing, this arrow is telling you, no, my initial point is 1 plus I, and my terminal point is 0. So I'm going backwards. So if you're going backwards, then it's called negatively oriented.
Now, what is negatively oriented?
It means that you start, your parameterization starts at the terminal point.
But is the equation negatively oriented or the actual line?
Or the curve. So
Which
this
one?
is, I mean, the way I think about it is right now, if you're given this line with the direction on it, then it's the parameterization that is negatively oriented. That's the way, this is the way I'm thinking about it in my head.
Right, okay.
Of course, you can rephrase all these things backwards and say, okay, here's a parameterization.
Sure.
And then I'll call this negatively oriented because it's going the wrong way. Because this arrow's going the wrong way. Either is, these are the same thing. So, if the path goes from terminal point to initial point, well, I want to say the path, but we want to say that the parameterization is negatively oriented.
Just say that it's a negative
Yeah, then we got
orientation.
negative orientation. Well, we'll have to pick a convention going forward. As long as we understand it today, we're okay. Oh my gosh, time went by really quickly. Let me just say that it's a little more interesting for closed curves when we talk about orientation. So for closed curves, there is a preferred way of writing down the orientation. Namely, if, say, of a circle, you want to go in the counterclockwise direction. This is a convention here. Counterclockwise equals positively oriented for closed curves. And clockwise is obviously negatively oriented. Right? And this jives with the way we want to go around the circle. Right? We want that our e to the I theta, or here, 3 cosine t, 3 sine t, that's the positive orientation. Now, sometimes it's not quite as clear what counterclockwise means. For instance, we could draw some curve that looks weird. We can make it really, really nasty. Okay, and if you're at any given point, you say right here, if I just say, which way do you have to go to be going positively oriented? It's maybe not immediately clear. Right?
Really? Go to the left.
Whether that's true or not is irrelevant. Point is, I can make these things arbitrarily nasty, right? And make it harder and harder to figure out which way is counterclockwise.
Go to the left.
Going to the left is not always going to be the
I know, if
the
you were
right
on the
answer.
underside of one of those, it would probably be going to the right.
There's and this is right. I mean, this is not incorrect. The question is, can you always tell whether you're on the underside or not?
Sometimes.
Sometimes, right? Okay, if I draw another one. Let's see if we can make it really bad. Wait.
Oh no, that's still easy.
Fine.
Yeah.
What if I do this? What if I do this though? What if I cover up the sides?
Well, then it's not a closed curve.
No, I mean they're there. You just can't see them.
Well, then we don't know it's a closed curve, so we can't.
I'm telling you, it's a closed curve.
But I don't believe you.
So, so what do you do? Well,
You go to the left.
so it's actually a very interesting theorem in mathematics. It says if you have a simple closed curve, okay, so it doesn't intersect itself except at the terminal and initial points. If you have a simple closed curve, then there is an inside and an outside. Now, if you draw a nice simple closed curve here, it's clear. There's an inside, and there's an outside. How do you prove that?
Depends on your perspective.
My perspective.
Yes.
You create a point inside and say that that's inside.
What if
and then
that's
you
a
have to
courtyard?
say-
Then it's outside.
And then you create a point
What if the
that's
inside
not inside, so it's either on the line or on the outside.
What if the inside becomes the outside?
That's.
So we did in geometry.
I'm not even sure what that means. It sounds very, very deep. So
What if your
This is
house is
geometric
around
figures.
this and that's your courtyard?
here's the
That's
really
outside.
the complicated thing here is that it's too easy. Saying that there's an inside and there's an outside. I mean, how could this not be? Right? This is the problem. Sometimes in math things are so easily stated that you can't see how in the world you would even have to prove them. Right? But stating that is not proving that. Right? And this is actually a rather big theorem, and it has a name. It's called the Jordan curve theorem. And it's surprisingly difficult to prove. So he proved there's an inside and an outside.
Can
And
you use geometry though? No?
I won't say there's no proof. Geometry is used, but it doesn't solve the whole problem. But if you want to try, this is a good thing to try to do. So one nice thing is once you know there's an inside and an outside, if you're going counterclockwise along it, where's the inside? Always to your
left.
left, right? And it doesn't matter where you are on any of these curves, right? The inside is always to your left. So counterclockwise is positively oriented for closed curve, but if you don't like counterclockwise, it should be the inside is to the left. Okay, as you walk around the boundary. Okay, and what's the boundary? So the boundary is this line that we draw, right? The boundary is where if you went to one side, you're in, and if you went to the other side, you're out. All right. Okay, so we should stop there. Let me tell you a quick joke. There was a competition to see who could utilize fence material to maximize the amount of area, right, on a farm. So 3 different people were given a certain amount of fence, right? And they could arrange it in any way they liked to try to maximize the area. So, one person who didn't really know what they were doing just built a nice square and said, I think, I could make a rectangle, but the square is probably going to maximize the area. Right? And so this did okay. But then another person said, well, geez, there's a better geometric figure than a square if you want to maximize area. Okay, do you know what it is? The circle, right? So he made his out of a circle. He said this is the maximal way to do it. The third one, mathematician, He hardly used any of the fence material at all. Didn't even use, I mean, he just took a little bit of it, and he made a little tiny circle. And he was on the inside of it, and everybody came over and said, "What are you doing?" And he says, "I declare myself to be outside."